Hi, this is going to be some additional transient analysis of circuits in DC in response to switching changes. So if we have a circuit like this and the switch closes or opens at some point, then the steps to solving the problem would be first find the steady state solution for IL, or voltage across a capacitor, before the switch is thrown. So, I mean, this might be the steady state or not. So basically you need to find the current or the voltage before the switch is thrown. Maybe you have that because the question tells you that it's initially in steady state before that happens, or because it just tells you what the voltage is or gives you information to figure out what it was. Then, once you've got that, what you need to do is find the kind of value you want right after the switch is thrown. So this might be the same as the value that you already found before the switch is thrown. If the IL or VC was the value you want, then you're done. You're done already from the first part. So you've already got this step done. You're done this part already. Okay, but if not, then you'll have to use the fact that the current through an inductor and the voltage across a capacitor can't change instantly in order to determine what those values that you're looking for will be right after the switch is thrown. So for instance, in this setup, if we wanted to find out, let's say, the current going through this resistor right after the switch is thrown, we would figure out still the inductor current before the switch is thrown, and then after the switch is thrown, we would say the inductor current can't change, so that gives us information to figure out what this current must be right after the switch is thrown. Okay, so then what you'll do is find the steady state value of the thing you want. So the variable you want. So in this case, they're asking us for the current through the inductor for all time. So that would just be the inductor current. But again, if you were looking for the current through the resistor for all time, you would find out the steady state value of that at this step. And then find the time constant after the switch is thrown. And finally, write that for the value you're looking for, x at t is equal to one of these different forms. So something that kind of starts at its initial value and decays away and ends up at the final value after enough time constants have passed. You could rewrite this in different convenient forms. So this is the form that only has one version each of the initial and final value. Another way to write it is x at 0 plus x at infinity minus x at 0 times something. Or you could write it as x at infinity plus x at 0 minus x at infinity times something. So in this form, we have to have this term initially be there and then disappear after enough time passes, which means we want the decaying exponential term. And in this form, we want this term to start at 0 and then eventually go towards 1 as enough time passes, which is what this term would be. And if you were to distribute the exponential terms across these products here and then simplify, you can see that all these forms are actually equivalent. Depends on which version you feel like, which one you want to use in the moment. So write any of those things to get your final, your expression for the variable that you're looking for all time. So for this problem in particular, we're going to figure out the time constant before and after the switch is closed, and then we're going to find the current through the inductor for all time. So the time constant is going to be tau equals L over R, where R is the R seen by the inductor. Before switching, R equals 100 ohms. And after, R equals R1 in parallel with R2 plus R3, which is getting our calculator up here. I've done this calculation, I think. So let's just do that again. So 1 over 100 plus 1 over 168. And we get, 62.7. 62.7 ohms. Yeah, 62.7 ohms. So tau equals L over R equals 1 millihenry over 100 ohms equals 10 microseconds initially. And 1 millihenry over 62.7 ohms, which would be 160 microseconds after the switch is thrown. That doesn't seem right. 160, yeah. I guess we calculated this wrong. Yeah, so 1 milli divided by, oh, you know what? What went wrong here is that we did 0.01 instead of 0.001. That's it. So we've got 16 microseconds. That makes a lot more sense. Okay, 16 microseconds is the time constant after the switch is thrown. Before the switch is thrown, time constant is 10 microseconds. So going back to this, a higher time constant means that it takes more time for stuff to happen. So it's going to be longer before the inductor kind of runs out of energy, stuff like that. Before the switch is thrown, we have this lower time constant. After the switch is thrown, we've got this higher time constant. And that's because the inductor sees less total resistance, less equivalent resistance after the switch is thrown because we've added more things in parallel. And that means that it's going to take longer for the inductor to kind of run out of excess energy if it is putting that through a lower resistance and is kind of supplying the current there. Okay. So that's our intuition for why the time constant of an inductor is inversely proportional to resistance, unlike the time constant of an RC circuit. Part B here, find the current through the inductor for all time t is greater than 0. So for this, we have to figure out what the initial steady state solution is for the current before the switch is thrown. And then that'll be the value we want. So we've done step 2. Then find the steady state of it after. And we've got our time constant after the switch is thrown right there. So the steady state value before is going to be IL at 0 from the negative side, which is before the switch is thrown, we've just got 5 volts over this 100 ohm because the inductor acts like a short in steady state. So that'll be 5 volts over 100 ohm, which is 0.05 amps. So 50 milliamps. Okay, and that's directed down. All right, and IL at 0 plus equals IL at 0 minus. So by this I mean just before the switch is thrown, so like limiting to, so a little bit less than 0 time, and at time a little bit greater than 0 is the same because it can't change. So that's equal to 50 milliamps down. And what is the current at infinity? So at infinity, after we wait a long enough time, this is behaving like a short, and interestingly, it's shorting out these resistors over here, so it's actually the same. IL at infinity also equals 50 milliamps. So think about this. Once this is shorting out these resistors, which is what it's going to do in steady state, then we've got 0 volts there. So in fact, closing the switch in this case doesn't do anything. We've got 0 volts going between here and here, and since that's the bottom of these resistors, and the other side is the top of the resistors, we're not putting any voltage across them, so there's no motivation for any current to go through them, and it's just going to stay like that. So that means IL at all time here is, you could use the formula if you like, 50 milliamps, and we're going to have, 50 milli plus 50 milli times 1 minus e to the negative t over tau, but then the exponential parts cancel. Or viewing this formula, this term goes away, so we just have 50 milliamps either way. 50 milliamps down all time. All right, let's look at a different problem now. So this time we have a voltage supply here, and we're going to find the time constant again before and after the switch is closed. And so the resistance is a little bit different because we've got R1 and R2 now the same. We've got tau initial is equal to, or maybe let's say tau open is equal to L over R1, which is 1 millihenry over 100 ohm. And that would be 10 microseconds. And tau, when it's closed, would be L over R1 in parallel with R2, which is going to be 1 millihenry over 100 ohm. But then in parallel with another 100 ohm is going to be 50 ohms. So that should be 20 microseconds. Okay. Then the current through the inductor for all time, t is greater than 0. So what we're going to need is IL at the point just after the switch is thrown, which is the same as the current through the inductor just before the switch is thrown, which is going to be, as in the previous problem, 50 milliamp. And we're also going to need what the current is going to limit to, IL at infinity. Well, now if we have 50 milliamp from this one, then this one should also give us 50 milliamp after enough time has passed, and this kind of stays, sort of returns back to 0 voltage at the end there. So it's going to be 0 volts when there's another 50 milliamps going through from this one. Right after we throw the switch, this is not going to be 0 volts. If it has 50 milliamps going down through it, then that means there's enough for 50 milliamps from this one, for instance, but then this one can't be putting any current through it. So that solution doesn't work because we have 5 volts here, 0. If we had 0 volts here because this one has 50 milliamps, then there's a voltage difference across that doesn't match the current. So that means we don't have 50 milliamps from this. We must have 25 and 25 for us to get 50 milliamps going down, which means the voltage here is going to be half of the voltage difference we're eventually going to have. So it's going to end up being 2.5 volts. Anyway, all we're trying to say here is what happens initially, but by symmetry, you can determine once there's no current, once there's no voltage across this anymore, once it's reached steady state again, and we've got 0 volts there, then we've got 50 milliamps coming this way, 50 milliamps coming this way, and so from KCL, we've got 100 milliamps going down. And then we'll say that I L at t is equal to the 50 milliamps times e to the negative t over 20 microseconds plus 100 milliamps times 1 minus e to the negative t over 20 microseconds. Okay, our initial steady state going away and the final value showing up after enough time. Now, in this case, because the 50 and the 100 match up nicely, we might consider rewriting this in a bit of a different form. So maybe we'll take the 100 through there and let the 50s cancel out. So in our previous three forms, we might want to let this be written a little differently. Maybe this form is nicest because then we're going to have some positive numbers, but then we've got the 1 minus e sticking around. Guess we have that anyway in this form, so let's give it a shot. So then we have 50 milliamp times 50 milliamp plus going to be 50 milliamp times 1 minus e to the negative t over tau. And that should be the same as if we kind of factor out a 50 milliamp from each thing. So you could get that from this part too by adding the two things. And you see that we end up with 50 milliamp times 2 plus e to the negative t over tau. And by that I mean minus. Yeah. So we start off with 50 milliamps, and then we end up with 100 milliamps exponentially. Cool. All right. Now the third part of this is kind of fun. If instead of remaining closed, the switch is open again after 40 microsecond, I guess we could put this as 20 microsecond there. Then determine the new function for the current through the inductor for all time t is greater than 0. So what we're going to do for this, maybe we'll label this part A, part B, part C. We'll have the initial point is now what we had at 40 microseconds. And for that, what we'll do is we can say, hey, you know, right after 40 microseconds, maybe that looks better like that, is because the current can't change instantly, the same as the current right before 40 microseconds. And so that'll be the same as the one we just found here after we substitute in 40 microseconds. So that'll end up with a negative 2 up there. Great. So there's the current right before we reopen the switch. And then the current right after the switch has been opened for a long time is going to be the same as we found earlier. So that's going to be 50 milliamps going downward. So now all we have to do is stitch these together using the new time constant, the time constant when it's open. So we'll say that IL at t is greater than 40 microseconds is equal to, let's say, IL at 40 microseconds, like right after that. So that's the 40 plus microseconds we just found, times a time constant that's going to be decaying away, e to the negative, except here we have to make something that's going to start at a 1 at 40 microseconds. So we're going to say t minus 40 microseconds divided by the new time constant, which is 10 microseconds. And then we'll add in the, similarly, IL at infinity times 1 minus this. Okay, so we can simplify that a bit. At 40 microseconds from the positive side, we worked out that that is 50 milliamp times 2 e to the negative 2. And this maybe we'll simplify, if you like, into negative t over 10 microseconds times a, you could kind of carry the negative through and turn it to e to the positive 4 multiplied by e to the negative t, if you were really keen on doing that. Or just leave it like that, that's fine. 50 milliamp times 1 minus this thing. And so you could simplify some of this stuff out a bit because we've got this expression multiplied by the by 50 milliamps there, and then we have the same expression multiplied by 2 multiplied by 50 milliamps. So because the 50 and the 100 milliamp limits that we were going towards in this problem match up a little bit nicely, you can let this negative term there cancel out with one of these 2's and then end up with just this. So you might kind of prefer to write it like that. A little bit easier to write. But if not, then no worries. Anyway, so it's probably the most clear from this first step here. So the IL at t is greater than 40 microseconds, starts at the IL at 40 microseconds, and then moves towards the one at infinity, which now is again 50 milliamps, according to a function that is going to go from, according to an exponential function that has a time constant of 10 microseconds, the time constant when the switch is open. So that means that IL at all time is equal to the IL at t that we found for the first part until t is greater than 40 microseconds. So we'll say 0 is less than t is less than 40 microseconds. And it's equal to this second expression, as long as t is greater than 40 microseconds. Okay, and now we can check that this actually worked. So let's see if we can plot these functions. So how about we'll say I is equal to piecewise 0.05 times 2 minus e to the negative t over 20 e minus 6. And that's going to be the case as long as t is less than 40 e minus 6. And otherwise, if t is greater than 40 e minus 6, we're going to have 50 times 1 plus 1 minus e to the negative 2 times e to the negative t minus 40 e minus 6 divided by 10 e minus 6. Okay. So that's that thing that's multiplied by 50, and then we'll close out the piecewise function. So there's our I at t. So we have this thing if t is less than 40 microseconds, and this other function if t is greater than 40 microseconds. We can go ahead and plot that. From t is, let's say, 0 to 80 e minus 6. And let's see here. We said if t is less than 40 microseconds, then we should have this first function. And if t is greater than 40 microseconds, we have this other function. Oh, you know what we forgot to do? We said 50 instead of 50 milli. So 0.05. Yeah, there we go. That's a little better. And on this plot thing, we can go 0 to, let's say, current equals 0 to 0.1. Great. So the current that we've got through the inductor starts at 50 milliamps, and then it increases according to a time constant of 20 microseconds up towards the 100 milliamp, and then it decreases once we've closed the switch again with this faster time constant now towards 50 milliamp again. And because the time constant here is twice as fast, meaning we have half the time constant, then you see that we've actually decayed closer down towards the limit in this time than we were able to rise up towards this other limit in this other time. So that's it. Again, the summary of this sort of a situation: you use the resistance that the inductor sees, whether the switch is open or closed, in order to figure out its time constant. And the time constant is one of the pieces that you need, along with the steady state values before and at infinity, to figure out what your initial and final values are to sub into one of these functions. And then once you've done that, you can substitute into the functions. If you have a really complicated case where you've got multiple switching events, then you may use one of the functions to figure out the initial conditions for the next one, remembering the most common thing that you're going to forget in that situation is to shift around the time to still give you the e to the 0 at the start of the second piece. Yeah? So basically, in this case, that means subtracting off 40 microseconds from the time in the exponents. Thanks for watching.